So you guys want to hear something funny? This is the second time that I'm recording this today. The first time, apparently, I did not click record. So we're going to go do this again. All right, welcome to chapter 15, four-wheel drive and all-wheel drive components. Hey, if you got a four-wheel drive vehicle, that means you can go 70 miles an hour on ice. At least that's what people do around here. Doesn't mean you can stop any better. So, all right, let's get going. Four-wheel drive. Four-wheel drive systems come in a few different varieties. Depending on the type of vehicle you have, you might have a part-time or full-time four-wheel drive system. Purpose and function of four-wheel drive is pretty obvious. It's to allow all four wheels of the vehicle to get power from the engine or the transmission. And it's an upgrade from a two-wheel drive vehicle, which only powers two wheels. They do make vehicles that are 6x6, 8x8 when you get into like military vehicles or off-road specialty type vehicles. But this picture right here is of a Jeep. Alex, this is for you. This is up your alley with your old Willys. This vehicle here is a typical four-wheel drive vehicle. It's all-terrain, utilitarian. That was kind of the idea behind developing four-wheel drive systems, so we can have better power transfer to allow a vehicle to drive in slippery conditions and not get stuck. So four-wheel drive vehicles have to overcome a similar situation that your two-wheel drive vehicles do, and that is while turning through a radius, all four wheels are spinning at four different speeds. Therefore, there has to be some sort of mechanism in place, like a differential, if you're engaged in four-wheel drive, in order to have equal power flow without hopping or skipping. So part-time four-wheel drive vehicles, they do not overcome this challenge. All-time four-wheel drive vehicles do. So the difference between all-time four-wheel drive and part-time four-wheel drive is a center differential mechanism of some kind. And so what I mean by that is, we've already discussed differentials, and we understand now at this point that differentials allow for the inner wheel and the outer wheel of an axle to spin at different speeds while transferring power flow. So a part-time four-wheel drive vehicle does not have a center differential to allow for the front drive shaft to spin at a separate speed or a slightly different speed than the rear drive shaft. All-time four-wheel drive, all-wheel drive vehicles do have a center differential mechanism that allows for the front drive shaft to spin at a different speed than the rear drive shaft. The big picture here is, what is the vehicle capable of doing? Can we drive in four-wheel drive on dry surfaces, or can we not? Part-time four-wheel drive vehicles cannot drive on dry pavement. They can drive straight, perfectly straight, but as soon as you get into the slightest turn, you will start to have scrubbing and binding take place between the resistance between the front tires and the rear tires, trying to spin their drive shafts at different speeds. So your typical part-time four-wheel drive vehicle would be your pickup trucks, your average utilitarian, utility purpose pickup truck. So your F-150s, your Dodges, your Chevys, your Toyotas, etc. They're typically part-time four-wheel drive because the rear axle is engaged 99% of the time. That vehicle is driving in two-wheel drive, and the four-wheel drive option is simply for slick road conditions or off-road conditions where you're going to have a friction surface between the tire and whatever it is you're driving on that's slick enough that the tires, while locked in four-wheel drive, the front axle and rear axle can spin at slightly different speeds, and the operator of the vehicle won't notice it. No damage will be done to the vehicle because the slip is allowed to take place underneath the tires. Excuse me. So that's four-wheel drive, all-wheel drive, part-time, full-time in a nutshell. We're going to get into some of the componentry and talk about some of the layouts and the different configurations that these things come in. So four-wheel drive vehicles can either be rear-wheel drive normally, so two-wheel drive in the rear normal, or they could be two-wheel drive in the front normal. They don't necessarily have to be just like your average pickup truck where the rear axle is normally the axle engaged and we lock the front axle in order to achieve four-wheel drive. You can have power transfer to the front wheels most of the time and then drive power to the rear wheels in order to achieve four-wheel drive. As a matter of fact, most of your all-wheel drive vehicles that are on the road today are front-wheel drive. The rear-wheel drive, I'm talking cars, like SUVs and cars. Your big pickup trucks, that's not what I'm talking about. Your all-wheel drive passenger cars, SUVs, are typically front-wheel drive. And then the all-time four-wheel drive or the 4x4 action is locking the rear end in order to achieve all-wheel drive. And we'll get into that part a little bit more too as we get going. So componentry that's necessary in order to achieve four-wheel drive. You still have an engine, you still have a transmission, but you must have the addition of a transfer case. And so what a transfer case is, simply put, it's a unit that allows for power to be taken off in two different directions. So if you look here in the picture, I'm going to try to pull up my ability to draw on this. And let's see, so here we go. Okay, so we got power coming in down here. So the output shaft of the transmission is connected to the input shaft of the four-wheel drive unit, the transfer case. Power in two-wheel drive mode simply transfers straight through the drive line. It goes right through the transfer case, and it comes out the rear of the transfer case and heads to the rear axle. When engaged in four-wheel drive, the transfer case has a chain or gear mechanism that is engaged that allows power to flow to the second output shaft. So when you're in two-wheel drive, power is simply just flowing at a 1-to-1 gear ratio straight through the transfer case. When you are engaged in four-wheel drive, power flow still goes straight through, but we also have a chain or a gear set that is connected mechanically, similar to how a manual transmission has forks that slide and we lock like a synchronizer type assembly together, and we engage a chain or a gear set that allows power to flow out and then to the second drive shaft. Most manufacturers are using aluminum case and chain componentry internally inside of their transfer cases. In the past, if we go back 40, 50 years, a lot of these transfer cases from the beginning up until probably 1980s or so, in that era, they were cast iron and they had actual gears inside of them. And so they were very heavy, but they were very rugged. And as a matter of fact, a lot of these older style transfer cases are desirable amongst like high horsepower rock crawler mudding type truck guys. Excuse me, because they hold up to the strain, the torque, much better than a lot of these aluminum case and chain transfer cases hold up. So we'll talk about the failure of these componentries in the next chapter. But just to give you a little bit of idea, a common problem in these transfer cases is the fact that the chains themselves will start to stretch over time. And so that can be an issue. And we'll discuss some of those drivability diagnostic procedures and whatnot, uh, failure analysis in the next chapter. Excuse me. All right. So moving forward, let me wipe all this stuff off the screen. Clear my drawings. There we go. I'm getting a little bit better with this software. Feeling like I'm becoming a YouTuber. All right. So how do we control four-wheel drive units? There are two ways manufacturers allow the driver to have control over the four-wheel drive engagement. And this is typically on your part-time four-wheel drive. Your all-time four-wheel drive vehicles, they're just all-time. They sometimes give you the option for low, or like a traction control button maybe that'll be a part of the four-wheel drive system, where they'll have you primarily in like an 80-20 split of power, and then if you know click into a traction control mode, it might split it more uniformly, like 50-50. We'll talk about how these manufacturers are splitting power. It's very odd, and it can be a little confusing. So let's start with this. How do we control the engagement of four-wheel drive? We can do it electronically, or we can do it mechanically. Electronically is this, what's right in front of your screen here, right on your screen. We've got a selector switch. The selector switch is operated by the driver of the vehicle, and they give the computer an input of what they desire for their drive status. Two-wheel drive, four high, and four low. So the next option here is another example of, this is a General Motors product. You see the addition of the auto four-wheel drive. The auto feature on some of these earlier four-wheel drive vehicles that were electronically controlled in the beginning, this is not an all-wheel drive setup. This is kind of a hodgepodge where manufacturers were attempting to have an automatically shifting into four-wheel drive scenario. That's confusing, but basically in a nutshell, the system was very crude, very bulky. It didn't matter if it was a Ford or Chevy or Chrysler. These systems tended to be frustrating to consumers, and they usually didn't use this option. If you've ever had a truck with an auto feature and you had a situation where four-wheel drive had to be engaged, you probably felt a large clunk or a bang as the vehicle went from two-wheel drive into four-wheel drive. The reason for that is you had mechanical componentry, so you still had a shift fork that had to very quickly engage the transfer case into four-wheel drive as soon as it detected wheel slip. So if the rear axle was spinning and the front tires were not detecting any wheel speed, or there's a great distance between RPM, the computer's logic would command that four-wheel drive was engaged. Well, the problem with that is you're at park throttle, maybe more, maybe you're at wide open throttle trying to accelerate out into an intersection to get through traffic, and the vehicle decides that you're slipping too much, and it goes ahead and slams the vehicle into four-wheel drive. You want to talk about breaking components? You want to talk about your head smacking into the back of the seat? It's very, very rough design. It worked, but it did not work well. And so as we advanced in all-wheel drive automation, you started seeing more and more like clutch packs and viscous clutches incorporated. And we're going to discuss that as well here in the next few slides. We're going to get into it and talk about how manufacturers have kind of altered the four-wheel drive unit on these all-wheel drive vehicles to be more user-friendly. So if you didn't have an electronic feature, if you don't have an electronic feature, you have a mechanical means of engaging four-wheel drive. I personally prefer this system over the electronics just simply because it's simpler. It doesn't have as expensive of componentry. You're removing the computers from the ability to engage four-wheel drive. It's not necessarily better. You know, you got to think about consumers and what they want. They don't want to be bothered with having to pull a lever. They want to just push a button or have it automatically happen. And so you've seen manufacturers kind of get rid of this entirely. So here's another slide. I pull this one off the internet so that way you guys can see a better image. But we got 2 high, 4 high, neutral, and 4 low. So let's talk about that. We see 2 high, 4 high, neutral, and 4 low. What's the difference? What's the difference? What's 2 high? What's 4 high? It's not really high. It's should really say 2 normal or 4 normal. The transfer case is allowing the input shaft to spin at the same RPM as the output shaft when you're in 2 high or 4 high. So as the vehicle is driving down the road, the input to the transfer case, if it's spinning 1 RPM, you have a direct ratio to the output shafts. There is no gear reduction or multiplication taking place in 2 high or in 4 high. 4 low is a little different. Transfer cases have the ability to multiply torque. You do not see this on all 4-wheel drive vehicles. You tend to see it on pickup trucks and utility vehicles. Okay, so your big SUVs, like your Suburbans, your Tahoes, your Expeditions, etc. You tend to see it on bigger vehicles. What that 4 low is actually doing is applying a secondary gear reduction. It could be a planetary gear set, which it typically is. It can also be a simple gear set that's engaged. It depends on the transfer case and the componentry that's in there. But what we're doing is we're taking the input speed, which is really the output speed of the transmission. So the transmission's final gear ratio is sent directly into the transfer case. And then the transfer case has another gear reduction that takes place. So if we come in, let's say it's a 1 RPM input, we can have a 0.5 RPM output. That allows the transfer case to multiply the engine's torque even more. It's a way to cheat when you have a high load scenario. For example, you're at the boat launch, you're on somewhat slick surfaces already, you don't want high wheel speed, but you want high torque. You could place your pickup truck into 4 low while pulling your gigantic barge of a boat out of the water. And then once you're up out of the ramp onto flat ground, you can place that vehicle back into 2-wheel drive and carry on as normal. Where 4 high by itself may not give you enough torque to actually get the vehicle up the boat ramp and pull the vehicle out of the boat out of the water all at the same time. Another example, some people do this. It's not advisable, but I've seen guys that tow stuff. If they get into a really steep incline, such as maybe your driveway you live on is on the bluffs here somewhere in Peoria, and you've got a big car trailer and you got a big race car or something, and you can normally pull down the road just fine, but getting up your driveway kind of strains your truck. It's not quite diesel enough in order to pull the truck and pull the trailer up the hill. You can drop a vehicle into 4 low. You don't really want to do it if you've got an asphalt or concrete driveway, but if you've got a gravel driveway and you got to pull it up that 1/4 mile steep incline, it's not going to hurt anything. You're just going to go really slow. So the final feature here is neutral. Believe it or not, a lot of transfer cases have a neutral feature. It's a second neutral. So you have a neutral in your transmission. Whether it's an automatic transmission or a manual transmission, you have a neutral. The transfer case also can have a neutral feature as well. Now, where the neutral feature is valuable is when you're towing that vehicle. So if you have a Jeep, for example, and you also have a motorhome, one of those big, interstate motorhomes, like a bus. You see this all the time. driving down the highway, you see an RV flat towing another vehicle behind it. If you have a four-wheel drive vehicle with a manual, or it can be an electronic four-wheel drive unit, it works a lot better with manual ones because there's no key on in this scenario. You can put that vehicle in neutral and disengage the transfer case from the transmission. You have to pay attention to how that transfer case is lubricated, because if it needs the input to spin in order to splash lubricate and or run a hydraulic pump, you have to be mindful of that, because you cannot flat tow that vehicle if it needs the input of the transfer case to spin in order to lubricate itself. All automatic transmissions need to have the engine running in order for the automatic transmission's fluid pump to spin. And so you cannot tow an automatic transmission vehicle with its drive wheels on the ground and just simply pop it in neutral. You have to disengage the transmission entirely if you're going to have its drive wheels on the ground. Otherwise, it won't lubricate. So it's a trick that people do. If you have a vehicle with a transfer case that you can pop into neutral, a lot of times you can get away with flat towing and not have to worry about it. Now, that's not always the case. You have to know exactly what you have for a transfer case. There are arguments on the internet, internet warriors that swear up and down their vehicle can be flat towed, and then you go look it up in service information, and sure enough, it can't be, even though it has a neutral feature, because it has to have the input to spin. The input shaft on it has to spin in order to spin the hydraulic pump. There's a lot of variations out there, but in a nutshell, most manually engaged part-time four-wheel drive vehicles have a neutral and a four-low. Not guaranteed, but most of the time they do. If you have an automatic part-time shifted, it probably still has a neutral and a four-low. It's just one of those features that's very common in your four-wheel drive vehicles. So let's talk about how do we engage the front axle. So the transfer case, it engages the front drive shaft, but it does not engage the front axle. So terminology here. Let's come back and look at this slide. Front drive axle, rear drive axle. The transfer case has to be engaged to allow the front drive shaft to spin. And in addition, there is a secondary lock-up mechanism on the front axle. I have yet to see a manufacturer that allows the front tires to spin the front drive shaft as you're driving down the road when you're in two-wheel drive. You have to think about the componentry here for a second. Transfer cases simply engage the rear drive shaft and the front drive shaft to achieve four-wheel drive. When they're in two-wheel drive, only the output to the rear shaft is engaged. This to the front drive shaft is disengaged. So if it was disengaged internally in the transfer case, but still mechanically linked to the front wheels, that front drive shaft would spin 100% of the time. You might think that's not a big deal, but it is. You have a parasitic loss in fuel economy when you're forcing the engine to drive a vehicle down the road, and then in reverse, you have tires that are the front wheels are being parasitically drained down in energy. They have to push not only the tire, but then they have to push the front axle, and they have to push the front drive shaft for no reason. It is a horsepower eater. Horsepower equals fuel mileage. Gasoline burnt equals horsepower. And so if you're wasting 5 horsepower even just to spin the front axle, that's fuel economy. That's like rolling down your window and throwing money out it as you're going down the highway. it's a total waste because it's not necessary in two-wheel drive to have the front axle locked in. So all manufacturers have some means of disengaging the front axle from the front drive shaft. In the beginning, it was done with mechanical hubs. So here we have an image of a Ford. Fords were common with this. Jeeps had these. There's all kinds of different manufacturers that use it. Chevy used them. You saw them on like Dana, like the terminal like Dana axle or whatever. Because all manufacturers back in the day used other, axle companies' axles. They just contracted with them, and so whatever. So this is a mechanically locking hub, is what's in front of us here. Mechanical locking hubs are very simple. They're not electronic. They don't have any type of levers or vacuum lines or wires or anything going up into the cabin of the vehicle. You simply click this red dial into the lock position. And then you walk around the vehicle and do it to the other side, just on the front wheels. Then you go back into the truck, you place the vehicle in four-wheel drive, and you start driving. After one or two rotations of the tire, those front hubs will lock in. When you want to disengage, you put the truck in two-wheel drive, you put it in park, you get out, you unlock one hub, you walk around, you unlock the other hub, and you get it back in the truck, and after a few rotations, it unlocks. Down the road you go. I just described to you the problem with these hubs. How many of you want to get out in the snow or in the mud or in the water, muck, walk around to the front of your vehicle through all that mess and engage your four-wheel drive? Nobody wants to. Can you see why these things fell out of favor? They're simple to replace, they're simple to fix, they're cheap. All those things are in the right order. But there's another problem. These locking hubs had to be pre-engaged before you actually needed four-wheel drive. So what I mean by that, when do we typically decide to put the vehicle in four-wheel drive? It's when we're slipping and we're stuck. So if I'm stuck in snow and I can't get out of my driveway, which means I can't move, the vehicle won't move, this system requires a couple rotations of the tire in order to lock. So if I'm stuck, I'm really stuck because I can't get four-wheel drive to engage if I can't get the front tires to spin. So you're left with one option. Get out your jack and start jacking up one side at a time and rolling the tire until it locks. Now, how many people actually want to get out and do that? Like 0 people do. If you even have the ability to do that. I could see that going negative. 1 million views on YouTube in the making. Another illustration, kind of how the mechanisms actually go together, just, whatever. So automotive manufacturers have gone away from the manual locking hubs. You'll still run into those vehicles. They're definitely still out there, especially if you end up working in like an independent shop out in a county somewhere. You for sure are going to find pickup trucks from the 80s, 70s, whatever, coming into your shop that are going to have broken hubs that are mechanical style. But if you're in a dealership or you're working in a more urban environment, you're probably going to see less pickup trucks anyway, like in the city versus out of the city. That's just strictly because pickup trucks are used more, like on farm use and construction, whatever, than they are in the city. People drive smaller cars and commute, stuff like that in the city. So it depends on where you end up living. But you will run across some of those mechanical lockers still, even though we're 30 years past the last time one was installed in a truck. So manufacturers have gone on to automatically controlled locking mechanisms. There's two ways that they've accomplished having a less invasive approach. So what I mean by that is from the driver's seat, we can now lock the hubs in. That's not new. That's literally, I had a 1988 Silverado that I did not have to get out. And lock hubs in. I had a truck at work that at one of the shops I worked at when I was in high school, that was a plow truck. It was a late 80s Ford, and it had mechanical lockers. As a matter of fact, that's how I first learned about mechanical lockers. When my first boss, they like to sit there and smoke cigarettes and point and laugh at me as I was, a 16-year-old kid not knowing what I was doing. I learned a lot the hard way, but one day I was trying to plow some snow in the parking lot and I was spinning like crazy. And he starts laughing and pointing at the front wheels of my truck, his truck, and I didn't know what he was talking about. I was in four-wheel drive. I moved the mechanical linkage into four-wheel drive, and I can't go anywhere. I'm stuck. That's when I learned about four-wheel drive hubs that lock. When he finally got done laughing at me, he got me out of the truck and showed me how to engage four-wheel drive hubs. So never hurts to have people like that in your life. So anyway, so manufacturers have switched over to vacuum and they've switched over to electronic locking mechanisms. There's a couple different ways we do this. Vacuum is illustrated in front of us. There's a vacuum line that runs up to the engine. I believe most of these are normally with the engine running and having vacuum applied. Vacuum is normally applied to these to achieve to achieve two-wheel drive. In order to achieve four-wheel drive and make it actually move and lock, the vacuum is taken away and the vacuum that is currently in it is vented. So you achieve like naturally atmospheric pressure, and then a big spring basically pushes the hub over, and this is the hub. So this photo shows the damaged teeth of one of those hubs that's caused by low vacuum due to a faulty vacuum check valve at the reservoir. Partial engagement causes a rattling noise, and it causes the teeth to get chewed off. A little difficult to see. I brought this picture in off the internet to give you guys a little bit better idea of what I'm talking about, but if you look down in there a little bit deeper, you can see there's a second part to this. So the first part is, all those splines. The second part has another set of splines. And the way this guy works is vacuum is applied, and the inner portion, you can see this little white part, and then another black ring. That black ring stays stationary, and basically where that white seal is, that's like the piston seal. So this inner part is allowed to travel. And it slides over identically to how a blocker and like speed gear work in a manual transmission. So when I want four-wheel drive, it slides over and it engages the uh, the the CV axle. So there, I went the wrong way. So the CV axle also has a mating gear set spline that in one direction when that hub moves, it locks it to the actual wheel hub where the actual tire is bolted onto. And when you want to disengage it, it pushes it away. So that way the wheel spins freely and the CV axle just sits there and it's not engaged. So the CV axle stops spinning. When it's disengaged, the CV axle begins to spin when that hub slides over and engages in the spline teeth, the grooves. So Ford, I'm picking on Ford a little bit. Ford has some pretty robust systems, but they really screwed up this component on like the mid 2000s, early. I don't know when they finally got this fixed, but it was somewhere in the late 2000s. I've done a lot of these. If you have a Ford with this vacuum setup, pay attention when you have one that fails. Pay attention if water comes out of that vacuum line. If water comes out of that vacuum line, that means this switching valve, this is the switch valve for the actual vacuum on off. It's just an on off valve, a little magnetic plunger, and it moves and allows vacuum from the intake manifold to connect and make its way all the way down to that hub. If you have a truck that has water down there and you do not have this little hat, so this little hat is, draw it on there. Talking about this little piece right here, this black part, that is aftermarket. That was a afterthought from the Ford engineers. When they first designed the system, they mounted that switch right on the firewall. Look above it. What is this area? That's the cowl. What comes from up there when it's raining? Water. Where does the water go? right down here. With a little bit of age, those vacuum lines become compromised, and even the vacuum switch becomes compromised, and water, saying that very, very precisely, water is able to dribble by gravity down here. And the water gets in that hub and it rots it. It causes rust. It destroys the seal. And before you know it, you've got a hub that's making a whole bunch of noise. So I said it sarcastically, kind of on purpose, because it's like really obvious that this would happen. But all manufacturers have the same problems. Doesn't matter which product line it is, which manufacturer, they always have oversights on these type of little things that we find later and make fun of them for. But this little hat that's on there, if you have a vehicle that has a four-wheel drive hub issue and there's water in the hose, go and check the other side. It's probably got water in it too. And then go up on the top of the passenger side with the hood up on the firewall and look and see if that little hat is there. If that little plastic cover is not there, you need to buy one as part of the job and install it. And it's a pretty good chance for the CYA here, you're probably going to want to do both hubs and that switch and that hat. Because if you've already got water down on the other side and it's not making noise yet, it's probably going to start making noise pretty soon. You can explain that to the customer. You don't necessarily have to sell the other side, but you can let them know, like, it's been compromised. So while it's here, would you like us to do both? If not, it's a ticking time bomb. It could last 100,000 miles, or it could break on the test drive when we finish the other side. You just don't know, but at least you're giving them a heads up, and maybe they can budget for it and come back and do it in a couple paychecks or something, if it's still going. But Dorman makes this part, and there's like 20 different aftermarket companies that make this little hat. As a matter of fact, Ford, I'm pretty sure if you buy the Ford Motorcraft part, you get that hat with the new switch. I don't even think they sell it without it, because there was a big warranty issue on those, and lots of people had a beef with Ford at the end of that, naturally. So let's get into more of the all-wheel drive vehicles. So the full-time four-wheel drive is sometimes called all-wheel drive, because full-time four-wheel drive is all-wheel drive. You can't have full-time four-wheel drive and not call it all-wheel drive, because it's always engaged. So the difference between part-time and full-time is we incorporate some sort of differential component in the middle of the vehicle between the front axle and the rear axle. Not all-time all-wheel drive vehicles are a 50-50 power split between the front axle and the rear axle. Believe it or not, most of these all-wheel drive vehicles are not truly four-wheel drive. They're a power split of maybe 70% to the front and 30% to the rear, meaning that they can't actually transfer 50% of the engine's torque to each axle. If you're dealing with a truck like an all-wheel drive Yukon Denali, it's basically a Chevy 1500 pickup truck. Its transfer case is actually a four-wheel drive unit that has a center differential built into it. So when you're in four-wheel drive, you're in four-wheel drive. You literally are in four-wheel drive like a normal pickup truck, and you can drive it on the interstate 80 miles an hour around curves and never have any type of bind-up issue. A lot of the componentry looks identical to a normal pickup that's just part-time. But the transfer case itself is designed in such a way that it can handle it can split the power between the front drive shaft and the rear. This component right here is a viscous clutch. Now, manufacturers go about this several ways on your lighter duty vehicles. Lighter duty meaning like your little Toyota RAV4, right? Your pickup truck. Toyota Tacoma. I don't know about the Toyota Tacoma. That's an actual transfer case. But your little SUVs, your sport utility crossover things, your all-wheel drive cars that are four-door sedans that they say all-wheel drive. They're not actually all-wheel drive. What they're doing is they're incorporating a transaxle on the front wheels that has a power takeoff. It's the best way to put it. It's a power takeoff, so it's another drive shaft that comes off of the transaxle and heads in a straight line towards the rear axle, but between them is a viscous coupling device like this illustration in front of us. And what a viscous coupling device, simply put, is a clutch pack component that has a fluid inside of it that is either electronically squeezed together or by fluid dynamics with heat, the fluid expands, thus squeezing the clutch packs together. So you're not really in all-wheel drive. You just have the ability to get into a various state of all-wheel drive. There are over 100 different designs, okay? So let's just get that part like clear. The book talks about a handful, and it's more on the theory side, and that's perfect for where we're at on this. We don't want to get into system by system. It's too confusing. You can look at a Ford, you can look at a BMW, and not be able to tell like what you're looking at until you spend some time and actually go through service information and learn about the componentry. And this is where manufacturers will send you to school to get extra training if you're working at a dealership, right? So you can learn about the actual systems that are sold on those cars, because there's not one exact system. If you look at your old school four-wheel drive, your old school part-time four-wheel drive, every manufacturer's looked exactly the same. There weren't that many variations. When we get into all-wheel drive, it's crazy. So here's an illustration, again, of a part-time four-wheel drive vehicle. Typical four-wheel drive vehicle that uses a longitudinal engine and a transfer case to send engine torque to both the front and the rear axle. I like how it says, even a four-wheel drive vehicle can get stuck. That is correct. Ask me how I know. You ever bounce off the rev limiter in a Duramax? Makes a lot of noise. So, typical layout of componentry in a transfer case. The textbook has like 4 or 5 different pictures. Go through those and have a look. A lot of you already got through transfer cases, which is good. I'm glad we got through that part at least, so you have an understanding of how these pieces go together with the chains, the gears, and all that stuff. So I'm going to kind of skip through this just a little bit because we've already done it in lab. There's the oil pump that's found on a lot of these newer units. Newer, I mean last 20 years, the older stuff. So here's one of the ways to tell if you got a pump. This is just a trick that I've learned. If the transfer case takes a very thin weight oil, it probably has a pump. If it takes a heavier, thicker gear type oil, like an 80-90 weight versus like a transmission ATF, it probably does not have a pump. That's from my experience. There's no book written on it, but if you think about it, even from theory, how can you pump an 80-90 weight oil? It's about impossible. I'm sure it can be done, but it's not. I've never poured that thick of an oil into a component that had a pump. Now, your thinner ATF type stuff definitely does. Now, on that note, on fluids, also keep in mind, manufacturer spec is what you put in these things. I've seen it many times where transfer cases come in for service and you pull fluid and it's the wrong kind. A lot of times you can tell based off of the color. So, for example, a lot of these GM vehicles that are the auto track, that's the, I believe I'm saying that correctly, that's the auto feature, the auto button. They take a blue fluid. It's literally blue. It is not red ATF. If it is the non-auto version, it does not take the blue, it takes the red. And there's a special part number for that. So it'll say like ATF for red, like Dexron 3, And then I forget the other stuff's called, the blue stuff. It's kind of expensive. It's not like obnoxiously expensive. There's really no reason to skip because it's, I mean, they only take like 2 quarts anyway. So if it's like an extra dollar or two a quart, it doesn't matter. Pass the customer the cost and move on with life. Your encoder motor, this is just a picture of your encoder motor for your auto transfer cases. Encoder motors do have specialty procedures for installing them. We'll talk about that in the next chapter. But the encoder motor is typically what we call that big fat electric motor that physically moves the shift fork inside of the transfer case. So as we engage into 4-wheel drive, the encoder motor is basically just a stepper motor, and it moves 2 clicks this way to go 4 high, moves 3 clicks that way to go 4 low, and moves 5 clicks to go neutral. I don't know. It has certain steps, and it has a feedback circuit, so the computer knows that it actually made it into the set gear that it commanded it to go into. So in the next chapter, again, we talk about drivability and diagnostics of 4-wheel drive units. We'll look at some particular testing and diagnostic strategies for how to use a scan tool to determine whether or not you have an encoder motor that's broken or an internal part. If it's internal, it's expensive. All right, electrical diagrams. Electrical diagrams are fairly straightforward. We'll look at these more in the next chapter, but if you take a quick glance now, if you have an electronic 4-wheel drive unit, you've got an input. I'm being careful when I say this. So if we're working on a newer electronic, okay, so like if you go back to like the 80s before we really had computers, it goes from switch to transfer case. And there's big fat wires and big fuses the whole time. If you're looking at the electronically controlled, computer controlled cars and trucks that are 4-wheel drive, it goes from switch to module and then to encoder motor. And it could go from switch to body control module to transfer case control module. Like there could be extra modules in place. But long story short, if it's got a computer, it's going to have data lines of some kind. It's going to have micro switches up on the dash that control a little bit of current that then when the computer turns on, maybe to engage the encoder motor, it flips on a big relay, and the big fat relay is what actually carries the heavy current down to the encoder motor because those things do draw a decent amount of amperage, probably in like the 20 amp range, way more than your little tiny micro switch is going to carry. And that's one of the reasons why manufacturers stopped using big fat wires, and they added a computer in the middle to kind of reduce some of the overall electrical wire size on the cars. So but I'm not really sure what this slide is talking about, to be honest. If the center and front differentials split torque equally, an all-wheel drive vehicle can become stuck when one wheel loses traction. That doesn't really make any sense. Maybe I'm not looking at it correctly. But on that note, I have a video I'm going to show you guys about how ridiculous some of these all-wheel drive cars are. You go buy an all-wheel drive vehicle, you are not buying a off-road monster. You are driving a safer vehicle. Purpose of a lot of these all-wheel drive vehicles is not so you can go off-roading. Now, yeah, Subaru makes a really good all-wheel drive system that is really capable of getting into a slick environment and not getting stuck. Your BMW, your Audi, your whatever, your typical all-wheel drive vehicle, the all-wheel drive part is for safety. It's not for off-roading abilities. Now, what I mean by that is, when you watch these videos, you'll see what I'm talking about. It's kind of funny to watch the computer try to think its way through power distribution. So we have power transfer units, and then we have the torque biasing. Okay, so the power transfer unit is like the front to back split. So if you look at this illustration here, we have a transfer case. I keep saying I'm getting transfer case, transaxle. It keeps going back and forth in my mind. Okay, you have a transaxle that incorporates a transfer case that has a power takeoff unit that is probably a viscous clutch of some kind. Okay, and so what this vehicle is doing is it's trying to, between the bias and the power takeoff, what it's trying to do is send power to the tires that have traction. That is basically all-wheel drive in a nutshell. We're trying to send power to the tires that have traction. So take a look for a second at the rear axle on this vehicle. This rear axle, it's probably an open diff. Most of these manufacturers that are using all-wheel drive are actually using an open differential. And so what an open differential is basically if this tire on the left is on a sheet of ice and I go to accelerate, that open diff is going to let 100% of the power go to that tire that can just spin freely. The tire that has good traction is not going to get anything. That's the nature of the beast with an open differential. But when we take an open differential and we incorporate advanced electronic controls, what we can actually do here is monitor the wheel speed and say, hang on, timeout. This tire is spinning at 2000 RPM and the rest of the tires aren't spinning at all. Logic would say it's on a sheet of ice or it's on snow or something like that. So, what the manufacturer can do with biasing power flow from the right and the left wheels, it can either via a brake component, such as like your analog brake system, it can go ahead and clamp down on that tire's brake and stop it, which then forces power to move to the other side that does have traction. And happy face, you get to start moving down the road. Likewise, with viscous couplings, some manufacturers put viscous coupling devices in the differentials. And it's not like a limited slip necessarily, it's electronically controlled mechanisms that kind of like sort of work like a limited slip axle, but it works in conjunction with the entire drivetrain, not just the one axle. And so now if I have one tire spinning a little too fast, I can let that clutch pack actually slip a little bit while still giving the other side 100% friction lockup and transfer some of that power to the tire that actually has traction. Front to back, it can happen in the same regards. If I have a viscous coupler that is in line with the rear drive shaft, I can apply or release torque to the entire rear end of the vehicle. So let's talk about the safety aspect of this. How is this system a safe vehicle versus a off-road monster? Think about the average panic situation where somebody is swerving or they're on slippery surfaces like on a sheet of ice and trying to do a panic stop and maneuver around a truck that just slid out. These systems are smart enough to balance the power flow between all four wheels. There's the all-wheel drive part. They're all-wheel drive because it can balance power to all of the wheels. Make sense? Not really off-road four-wheel drive type vehicle. And now componentry, from the front to back, right to left, the power splits. Well, typically, like the front axle will be even and the rear axle will be even. That's not typically. That's 100% correct. The front axle has the ability to put out equal power between each front wheel. The rear axle has the same ability to put out equal power from each right and left rear wheel. Now, front to back is where we get a slight variation from make and model. So some manufacturers do a really good job of splitting power between the front and the back to like 50%. Some manufacturers can only give maybe the rear 60% and the front 40%. They can't actually get a 50-50 split because the clutch packs in their design are not built to allow for all-time all-wheel drive. They're only allowing the like rear axle to engage during a situation when it absolutely needs the rear end engaged to assist the front axle. So when I talked about in the beginning, like your auto button four-wheel drive units, that's kind of what they were attempting to do with that, is this scenario. So when a driver of a vehicle is experiencing wheel slip and trying to accelerate at the same time, it would go ahead and lock in the four-wheel drive unit very violently and crudely. In As we've advanced into what I'm talking about now with all-wheel drive, we're doing it the same thing. We're trying to accomplish the same goal, but we're doing it with viscous clutches. And so clutch packs have more give. They're not going to be a violent gear on gear spline linkage bang, into motion. There's a little bit of give because it's friction, it's fluid, it's paper disc, metal disc, and oil. And you're not going to get a violent lock. You're going to get a little slip in a worst case scenario, which will cushion that engagement and not freak out the driver of the vehicle. If you have one of these vehicles and you haven't experienced it yet, give it a try. It's not fun. All right, let me get this off of here. Let's move on. We're getting close to the end. So here's just a couple pictures and illustrations. That's a viscous coupling device right there, believe it or not. It looks like a gigantic muffler or something, spaceship, flux capacitor, I don't know. But it's a viscous coupling device. You will find those at the front of the vehicle. You'll find them at the back of the vehicle, but they're always going to be somewhere on a driveline component. You're not going to find them like in the trunk unless it's one that was replaced and it's a core and it's going back to the dealership. Another illustration of biasing my power and my torque. And then the textbook has a couple pictures that you can go through and look at about the viscous clutch componentry and the ECM's controls. But basically, in a nutshell, what we have here is a very similar component to a clutch pack in an automatic transmission. So an automatic transmission utilizes that paper, steel, whole bunch of these components all together. And when I apply hydraulic fluid to it, I squeeze them together. And when I squeeze them together, I lock one to the other. So the drive shaft to rear, the drive shaft from front are able to slip until I lock those clutch packs together. And once I lock them together, I get a power transfer. And I move typically at 1-to-1 right through. If they're designed to slip a little bit, it might be 1-2.7. That's how they're maybe getting a little gear reduction, not gear reduction, but a split in gear torque, whatever. Moving on. So it can be done with fluid. It can be done with stepper motors. And I'll tell you this, I have not talked to anybody in a dealership that has not seen like a lot of these type of failures. They're If you're not nice to them, they're going to burn up. If you're an aggressive driver, you're going to destroy these things. Just plain and simple. They don't like they're a wear and tear item. They only have so many applications, so much slipping that they can take before they just simply wear out. Not that they're necessarily like expensive. Some can be expensive. Labor wise, depends on where they're located. But I've got a video from South Main Auto that I'm going to include in this lesson. And he has a diagnostic little thing. I'll let you guys watch that. It's quick. He replaces a viscous coupler that's on a differential. And some of you in class that started working on differentials, that donation we got from Nissan, actually a lot of those had this viscous clutch component bolted onto the input. So where the pinion shaft came through into the differential, on the outside of the case, you saw a viscous clutch component like this. It just goes to show how common this technology is. So a few last things kind of hit on here. We've got a front drive shaft, the actual outboard joint on a four-wheel drive vehicle. They can either be a U-joint style or they can be a CV shaft style. So this is your independent suspension. And this is more of your solid front axle. So keep that in mind if you're working on servicing worn out, popping, clunking componentry. These can be kind of a trick to get apart. They're not that bad, but labor rate, you're making money, so what does it matter? CV axles pop out of these four-wheel drive trucks and SUVs, just like the front-wheel drive CV axles on a passenger car pop out. They're really not that complicated. Once you get through a few of them, you figure it out pretty quick. One final note on locking. This slide should have actually been like way in the beginning. I don't know why it's back here. But this is a illustration in your textbook. Textbook has this as well. This is an illustration of the actuator that's on the front axle on your either electric or vacuum controlled front axles in order to disengage the front drive shaft from the front tires. Typically, we disengage the front drive axle. So we split that axle power flow. So you can see in the illustration here, we've got an actuator, and then we've got a vacuum actuator. So we got an electronic version, and we've got a, I mean, maybe that's a vacuum one, but whatever. It can be electronic, it can be vacuum. But we're basically just sliding the blocker and sleeve assembly over to engage the axle. It's straightforward. Look at the illustration, and you can go from there. So the rest of this is basically, these are all the pictures in the back of your textbook, how to replace a hub assembly. I'm going to put some of that stuff on YouTube for you guys to watch. And in the next chapter, so we're getting down to the wire here. Believe it or not, I think we're like 4 weeks out. Is this week 4? I can't remember. It's taken me 4 weeks to try to come up with a new way to record these videos because I don't like the other way. I don't like how it's going, especially if we're going to be doing this for summer. I'm going to come up with something a little bit more efficient for my time. Those videos take a long time to upload on DSL internet, tell you what. But maybe with this format, it'll go a little quicker. But in the next chapter, we're going to get into diagnostics. And then after that, we're going to get into noise, vibration, and harshness. It's basically all the vibration stuff that I don't really care about, like 90% of it. But when you're buying an $80,000 truck and it makes a slight little humming noise, you're going to want it fixed because you just dropped a whole bunch of money. You're making house payments on the truck. And you expect more out of General Motors, Ford, Chrysler, BMW, whoever. And so there's a lot of noise, vibration, harshness stuff we're going to talk about. Then at the end, probably the last lesson, I'm going to go through ASE, some reviews for ASE, and go through some more like actual case study stuff that is not in the textbook. So if you have any questions, concerns, comments, complaints, get a hold of me and let me know. Thank you for tuning in. Hopefully you like this format. Hopefully the audio is decent enough. This is the best microphone that I have. Very cool. It's a gamer setup. It's like one of the first times I've actually used the microphone. So anyway, now you're all going to stare at me awkwardly as I try to figure out how to actually shut this off. Somewhere I hit stop. Stop share.